In the last period, we have seen angular velocity. Today, we will see the expression for time period. Expression for a time period of a particle performing a circular motion. Consider a particle is performing a circular motion along the circumference of the circle of radius r. A is the initial position, B is the final position. That is, a particle travels from A to B in a time of t second. Theta, the angle described by radius vector at the center of circular motion is known as angular displacement, that is a theta, and omega is the angular velocity. It means a particle is performing along the circumference of the circle with constant angular velocity, that is omega. So, by definition, angular velocity is defined as change in angular displacement upon time. Angular velocity omega is equal to change in angular displacement upon time. Change in angular displacement is theta. So, omega is equal to theta upon t. When this particle completes one revolution, suppose this particle completes one revolution, the angular displacement of the particle will be this 90 degree, this 90 degree, second quadrant, third quadrant 90 degree, and fourth quadrant 90 degree. It means this total angular displacement of the particle is 90 plus 90 plus 90 plus 90, that is 360. That is, particle describes an angle 2 pi at the center of the circular motion. So, angular displacement is 2 pi. And by the definition of a time period, the time interval required to complete one revolution, that is called as a time period. So, small t, time taken by the particle to complete one revolution, will be equal to capital T. Then put these two values in above equation. Omega is equal to theta upon t, but theta is equal to 2 pi. Small t is equal to capital T. So, omega is equal to 2 pi by t. And t is equal to 2 pi by omega. So, this is an expression for the time period. We know the relation between time period and frequency is that they are reciprocals of each other. That is, time period is equal to 1 upon frequency, or frequency is equal to 1 upon time period. So, time period is the reciprocal of frequency. So, substitute this value t is equal to 1 by n in this expression. So, this t is equal to 1 by n and 2 pi by omega as it is. So, n is equal to, after reversing, so n is equal to omega upon 2 pi and omega is equal to 2 pi n. So, this angular velocity can be expressed in terms of time period as well as angular velocity can be expressed in terms of frequency. Here, the next article is angular acceleration alpha. Before going to study the angular acceleration, we will see linear motion. What happens in linear motion? When displacement is changed, velocity is generated. When velocity changes with respect to the time, acceleration is produced. It means change in displacement causes the velocity, and change in velocity causes the acceleration in linear motion. In the same way, when angular displacement changes with respect to the time, angular velocity is created, angular velocity is produced, or when there is a change of angular velocity with respect to the time, then angular acceleration is produced. So what are the examples of this? If we switch off the fan, as we switch off the fan, its speed goes on decreasing. Continuously its speed goes on decreasing and finally it comes to the rest. It means angular velocity is changing. As the number of revolutions per second is changed, angular velocity is changed. As angular velocity is changed, there is a generation or formation of angular acceleration alpha. Or if we switch on the fan, then the speed of the fan goes on increasing. As the speed increases, then angular velocity also increases. As there is a change in angular velocity, an angular acceleration is produced. So angular acceleration is defined as it is the rate of change of angular velocity with respect to the time. It is the rate of change of angular velocity with respect to the time. We'll consider the case in which omega 1 is the initial angular velocity, omega 2 will be the final angular velocity. This angular velocity changes from omega 1 to omega 2 in a time of t second. And as it changes omega 1 to omega in a time of t second, the angular acceleration produced in that motion is given by angular acceleration is equal to change in angular velocity upon time. So what is the change in angular velocity? Change in angular velocity is a final angular velocity minus initial angular velocity. So alpha is equal to omega 2 minus omega 1 upon t, where omega 2 is final angular velocity, omega 1 is initial angular velocity. This omega 2 minus omega 1 gives the change in angular velocity. But omega is equal to 2 pi n. So omega 2 is equal to 2 pi n2 and omega 1 is equal to 2 pi n1. Substitute these values of omega 2 and omega 1 in above equation. Omega 2 is equal to 2 pi n2, we substitute here, and omega 1 is equal to 2 pi n1. After substituting and taking a common 2 pi, the equation will be alpha is equal to 2 pi in the bracket n2 minus n1 upon t. So the expression for angular acceleration alpha is a 2 pi in the bracket n2 minus n1 upon t. Its unit is radian per second square. As this angular displacement, radian is a dimensionless physical quantity. So its dimensions will be m to the power 0, l to the power 0, t to the power 0. Per second square, this will be t to the power 2. So its dimensions will be m to the power 0, l to the power 0, t to the power minus t. So these are the dimensions of angular acceleration alpha. So what will be the nature of this physical quantity? Whether this angular acceleration is a scalar quantity or vector quantity. As usual, if theta or omega is finite, as omega, angular velocity is finite, then this angular acceleration alpha is a scalar quantity, And if omega is infinitesimally small or theta is infinitesimally small, then this angular acceleration alpha is a vector quantity. But the sign conventions for alpha are just different from the sign conventions of angular velocity and angular displacement. So, no doubt, angular acceleration is always perpendicular to the plane of the circular motion. So, if this particle performs a circular motion, then angular acceleration will be perpendicular to the plane of circular motion. It will be in an upward direction or in a downward direction. But the sign conventions are slightly different. If the speed of revolution increases, as the speed of revolution increases, then alpha is taken as a positive and it is taken in an upward direction. When alpha is taken positive, when the speed of revolution increases, alpha is taken as a positive and it is in an upward direction. And when the speed of revolution decreases, as in case of switching off of the fan, after switching off of the fan, its speed goes on decreasing. Whether that fan is revolving in a clockwise direction or anti-clockwise direction, it do not make any difference. So, but only the quantity which is taken into consideration, that is that its speed decreases. As the speed decreases, alpha is in a downward direction and it is taken as a negative. So, the sign conventions for angular acceleration alpha are just different from angular velocity and angular displacement. In angular velocity, if circular motion is in an anti-clockwise direction, angular velocity omega is taken as a positive and it is in upward direction. When circular motion is in a clockwise direction, angular velocity is taken in a downward direction and it is taken as a negative. But these sign conventions are not used for angular acceleration, and the sign conventions for angular acceleration are: if the speed of rotation increases, alpha is taken as a positive, and if the speed of rotation decreases, then it is taken as a negative, whether that body is revolving in a clockwise direction or in anti-clockwise direction. These sign conventions, alpha positive and alpha negative, are used in kinematical equation. Please remember whether the sign conventions, which sign conventions are used. So, in a kinematical equation, which sign convention is to be used? As omega increases, alpha is positive. As omega decreases, alpha is taken as negative. This sign convention is used in kinematical equation only. But for the cross product, what are the sign conventions? It means just we establish the relation between angular acceleration r and tangential acceleration. Then in that case, we use the same sign conventions. If the particle is revolving in an anti-clockwise direction, alpha is taken as a positive and it is in an upward direction. And if a particle is revolving in a clockwise direction, then alpha is taken in a downward direction and it is taken as a negative. These sign conventions are used for cross product only. So, here we have to use two sign conventions in two different situations. If alpha is present in kinematical equation, then we have to use a sign convention in which as omega increases, alpha is positive, and omega decreases, alpha is negative. But the sign conventions are changed when this angular acceleration is used in a cross product. In a cross product, if a particle revolves in anti-clockwise direction, then alpha is positive, and if particle revolves in a clockwise direction, alpha is negative. So this is the difference in the sign conventions for angular acceleration. Okay.